So here we have Envision Algebra 2, 2.4, the prereq skills, because we're about to do 2.4, which is complex numbers. But the prereq skill in my mind that matters on this is radical simplification. Uh, it's taught in Algebra 1, it's talked about in geometry, and every year kids act like I've never seen this before in my life. Even some kid's going to just push buttons in a calculator and give me a decimal answer, which is rounded. Simplification is exact, same thing, looks different. So, I'll do a simple example before I jump into these. I'll talk about the square root of 8. Now, I used a small one because hopefully everybody understands that 8 is simply 4 times 2, right? So I can take the square root of 8, I can rewrite it as the square root of 4 times the square root of 2. Now, I know that the square root of 4 is 2, and I do not know the square root of 2. Neither do you. So I have 2 times root 2. That's the idea. I'm going to break these radicals into two numbers that I can take the square root of. And there's a longer way to do it, but I'm not going to talk about that way to juniors. But the idea is break the radical into two factors, one of which I can take the square root of. You don't have no idea what the square root of 128 is. But I do know that 128 is a 64 times 2, so I can think of it as root 64 times square root of 2. And I know, and you should too, because you're a junior in high school, that the root of 64 is 8. All right, next up is 54. I learned my multiplication tables in 3rd grade, just like y'all. Maybe it was 4th, but I remember learning them. I know that 54 is 9 times 6. So I'm going to break this down into a singular root of 9 times a singular root of 6. And I know that the square root of 9 is 3, so 3 root 6. Now look at this one that I put on here. The question is can you take the square root of a negative? A lot of kids think you can, and you actually can't. But can you take the square root of a negative and be real? The answer to that is no. But we can do a little bit so far, okay? So I know that 125 is 25 times 5. And I'm just going to leave that negative 5 in there right now. This would become 5 root negative 5. And the goal of the lesson today is how do we handle square roots or even roots of negatives. That's the goal today. The goal was not this stuff over here. This stuff over here was stuff you're supposed to already know. Now I know and you know you don't know because you've just been doing bare minimum through high school. It's evident in your test scoring. All right, so here is 2.4, which is complex numbers and operations. Our vocabulary is what's called a complex conjugate. I will define that later. I will. We have what's called a complex number, and this stuff needs to be defined. A complex number has a real part and an imaginary part. A real part that we call A, and an imaginary part that we usually refer to as BI. And it's written in the form A plus BI. All complex numbers are written in that form. And it's beyond the scope of Algebra 2 in Tennessee, but every number that exists is a complex number. Every number that exists is a complex number. Of course, I have kids that don't even know what rational numbers are. How did you get to Algebra 2? The imaginary number is a number denoted by I. I for imaginary, okay? And then we need to talk about I. So there's some things about I. I is equal to, I'll have to switch over to my pencil here. I is simply the square root of -1. That's what I is. That's all I is. It's the square root of -1. So let me go back to what I was doing real quick. I was stuck at that. I had 5 roots of -5. I can think of that as 5, and let me go off the side. Negative root 5 is simply a root of 5 times a root of negative 1. And a root of negative 1 is I. So I'd have 5 root 5I. Now, I don't like to put, when I'm writing the I at the end, I like to put it in the middle, 5I root 5. That's how I like to write them. If I was typing, I might put I at the end. There's some more to this. I'm going to talk about what I squared is. So let me come up with I squared. If I wanted I squared, I would square the left-hand side, which means I would square the right-hand side. And if I square a radical, I get the number inside. So I squared is negative 1. There's some other ones here. I'd like to know what I cubed is. I need you to understand that I cubed is simply I times I squared. That's all she is, nothing more. And I just learned that I squared was a negative 1. So I cubed ends up being negative I. And the other big one is I to the 4th. Well, I to the 4th is nothing more than an I squared times an I squared. And what was each I squared worth? Each I squared was worth negative 1. And if you take a negative 1 and you multiply it by a negative 1, you get 1 back. So these are definitely worth memorizing. Definitely worth memorizing. All right, pause for a second and I'll be right back. Now, I've taught Algebra 2 for a great many years. One of the things I'm always surprised at is how kids don't know what the opposite of squaring is. The opposite of squaring is and always will be square rooting. So here I have something really simple. I have x squared equals 16. Now, do remember that the 2 is telling you that there will be 2 solutions. You're going to have to use the plus or minus symbol. It's x squared. It has 2 answers. If I'm going to do this by square rooting, I'm going to take the square root of the left and I'm going to take the square root of the right. And I'm simply going to get that x is plus or minus 4. That was a real number. Now, there's also a little study tip down here. It says you can also solve that equation by subtracting 16 from both sides and then factoring. I mean, it's worth doing. Some people are just natural factors. Set it equal to 0. That factors as x plus 4 times x minus 4. We get to use a zero product property. X plus 4 is 0, or x minus 4 is 0. We shift right, both cases. X is, guess what, negative 4, or x is positive 4, which is exactly what happened here. Now let's look at B. When you do B, you're going to run into this issue. You're going to have that x is plus or minus the root of negative 9. So you're going to have to remember that I is the square root of negative 1. We're going to break this apart. We're going to say it's plus or minus root 9 times the root of negative 1. And then we're going to use substitution. This root of negative 1 is an I, and the root of 9 is a 3. So plus or minus 3i. It's really easy. It does blow some kids' minds. I know that most of you will never go into the field of electrical engineering, but you'll discover that that's why we actually need the imaginary unit. Without imaginary numbers, we do not have electricity. There's so much stuff that we don't have. All right, adding and subtracting complex numbers. This is easy as combining like terms. Which, I've got some juniors this year that can't combine like terms. They think x and x squared are the same. So I'm just going to highlight the like terms here. I'm going to have to put them together. I got to figure out what 4 minus 11 is. Well, that's negative 7. And then I've got to add to it the result of negative 7i plus 9i. Well, that's going to be twice I. Now, I do want you to remember this. It's kind of a big deal. I wrote it down in the notes a minute ago. Written in the form a plus bi. So we are written, your answer is written real plus imaginary. That's how we write them. And that's how that one was written. The real number comes first, the imaginary comes second. All right, what is the difference between 6 plus 8i and 2 minus 5i? Well, difference would be subtraction. So what we're thinking here is we're thinking 6 plus 8i minus 2 minus 5i. And more kids will miss subtraction and addition all day long because they will forget to distribute their negative. You got to distribute that negative. It's 6 plus 8i minus 2 plus 5i. And again, we're going to focus on like terms. We have a 6 minus a 2, which is a 4. And then we have 8i plus 5i, which is 13i. And again, we write it as the real plus the imaginary. So that one's in the right part. And there's your study tip. I mean, it's just like terms. Multiplication. Multiplication is going to be a little tougher. It is, because you have to know what I squared is worth. But we're going to use the distributive property. We're going to distribute it to both pieces. So negative 2 times 8 is negative 16. A negative 0.5 times 8 is negative 4. Negative 16 plus negative 4 is negative 20. So I get negative 20. Don't forget about the I. And this one will be a little harder here. Negative 2 times negative 9 is negative 18. Half of 9 is 4.5. Minus 22.5 I squared, because we have an I times an I squared. Now, you need to recall, I told you it was worth memorizing, I squared is negative 1. So let's work with this piece kind of off to the side. Negative 22.5 times negative 1 is going to be positive 22.5. Now, the only thing wrong with this is not in the form A plus BI. It's backwards. It needs to be written as 22.5 minus 20i. All right, move on to the next one. You know, what would Jesus do here? Well, Jesus would FOIL. I'm actually going to do the box method because why not? We have 3 minus 2i, and we have 3 plus 2i. 3 times 3 is 9. 3 times a negative 2i is minus 6i. 2i times 3 is positive 6i. And then 2i times negative 2i is going to be minus 4i squared. Now, let's think about that negative 4i squared. That would be a negative 4 times a negative 1, which is just 4. If you see an I squared, what you do is you change the sign and you just cancel out the I squared. That's all you do. Oddly enough, this one works out really cool. A negative 6i plus a 6i, they cancel, don't they? Let's write out what we have. We have 9 minus 6i plus 6i, and then plus 4. These guys are gone. We end up with 13. Now, the reason that this worked the way it did is because these two things are special. So let's go back and define something that I haven't defined. The complex conjugate. And it's really simple. It says the conjugate of a plus bi is a minus bi. We change the sign on the weird part. So the reason that these two things kind of cancel each other out and just reduce down to a solid number is because these two things were complex conjugates of each other. So the reason this worked the way it did is because 3 plus 2i is the conjugate of 3 minus 2i. That's why it worked. Kind of cool. Which probably brings us up to division. It does. It does bring us up to division. Come on, slide 6, BRB. All right, so how can you write this quotient in the correct form, which is a plus bi? You can do that with the complex conjugate. So, you know, the first question here is we're going to focus on the denominator. We'll focus on the denominator. The question is, what is the conjugate of 2 minus I? You know, you need to be thinking about that. So just pause whatever and think. I don't know how long it takes you to think. It is 2 plus I. What we're going to do, and you just saw what happened, if you multiply something, a complex number by its conjugate, you get a nice whole number back, right? So because we know that if we multiply a number by its conjugate, we get a, we'll say, nice number back. We can multiply 2 minus I by 2 plus I. Now, if I do something to the denominator for equality, I must do it to the numerator. That's just how math works. It's all about equality. That is literally the only subject that we teach that is probably about equality. So we're going to take our original rational expression, 10 over 2 minus I, and we're going to multiply both the numerator and the denominator by their conjugates. Now, you're supposed to be doing things the way your math teacher does. Notice how I wrap things up? Wrapping's a big deal. The numerator is nothing more than the distributive property. 10 times 2 is 20. 10 times I plus 10I. The denominator is going to take some work, and there are some shortcuts on this, but let's just switch gears. I like to go over some other alternate techniques. Let's do it this way. All right, let's do vertical multiplication. I times negative I is negative I squared. I times 2 is going to be 2I. 2 times a negative I is minus 2I. Don't forget your plus 0 that's there. And then 2 times 2 is 4. And then we add down. We have a negative I squared, we have no i's, and we have 4. Now, what do you know about negative I squared? You know that I squared is negative 1. So this is a negative 1, which is 1. So we end up with 4 plus 1, which is 5. Weird, huh? Now, can this be reduced? This rational expression has 3 terms, and each of those 3 terms are divisible by 5. You might view this as 20 over 5 plus 10I over 5, which would give you 4 plus 2I, which is the correct form. Or you might just realize that each piece is divisible by 5. 20 divided by 5 is 4. 10 divided by 5 is 2. 5 divided by 5 would be the understood one, which I don't need to talk about anymore. And what you are doing here is you are rationalizing the denominator. That's what this is called, rationalizing the denominator. All right, here's the try it, but of course you're watching a video, so I'm just going to do it for you. And again, my question to you would be simply, what is the conjugate of negative 1 plus 2I? You know, and you're thinking, right? The only thing that changes is the weird thing. And that's the deal. For conjugates, I don't care what kind of conjugate it is, you change the sign on, and I say this, on the weird piece. 2I is imaginary. It's weird, right? It's weird. So we change the sign on that. Now we're going to do the same technique. We're going to multiply the top and bottom by negative 1 minus 2I. Notice the usage of parentheses. They're a big deal. I'm even going to go back and wrap up here. And this one's going to be a lot harder than the last one. I'm going to do foiling here. I'm not going to do vertical multiplication. And I'm going to focus on the denominator first. Negative 1 times negative 1 is 1. Negative 1 times negative 2I is positive 2I. Negative 1 times 2I is minus 2I. Notice how those pieces cancel? That's always true when you multiply a number by its conjugate. And then 2I times negative 2I is minus 4I squared. It's very common to forget about that I squared. I don't know why, but that's just what kids do. All right, up to the numerator now. 4 times negative 1 is negative 4. 4 times negative 2I is minus 8I. Negative 3I times negative 1 is plus 3I. And then negative 3I times negative 2I is positive 6I squared. So let's focus on these pieces, right? I just talked about it a minute ago. If you see I squared, throw it away, change the sign. That's a -6. If you see I squared, throw it away, change the sign. That's +4. That's legit how hard this is. Legit. All right, like terms, we have a -4 and a -6. That's going to make -10. We have a -8i plus 3i. Last I checked, -8 plus 3 was 5. Don't forget the I. Down low, gone, gone. 1 plus 4, 5. And hey, we have a situation where we reduce again. These three pieces of this rational number, I called it an expression earlier, but it's a rational number, of this rational number are all divisible by 5. 10 divided by 5 is 2. Don't forget about your negative symbol. 5 divided by 5 is 1. And in mathematics, ones are understood. So I don't need to say 1i. Can I? Yes. Should I? No. Anywho, last slide. How can you solve x squared plus 4 using factoring? It's a little harder to do, to be quite honest with you. This is a monomial, well, whatever. It's a binomial, it's got two pieces. It's going to factor with actually a double set of parentheses. Everybody should know that those two create x squared. That's the goal. Maybe think of this as x squared plus no x plus 4. The outside pieces have to make 4, but, and it's positive 4, add to 0. Okay, so this is why it's fun. Not really. I know that 2i times a -2i is going to be -4i squared. I know that I squared is -1, which means that's 4. One of these is 2i, and one of these is -2i. And I want you to notice how these are conjugates of each other, because they are. The conjugate of x plus 2i is x minus 2i. Notice they're conjugates. Now, that's going to be a little hard for kids who've just seen complex numbers for the first place. But that's how you do it. So now we're going to use ZPP, zero product property. X plus twice I is a 0, or x minus twice I is a 0, both one-step equations. This would tell me that x is -2i, and this would tell me that x is +2i. And again, notice that these are conjugates. Imaginary numbers always occur in what we call conjugate pairs. All right, you having fun yet? Last one. To make a 9x squared requires a 3x and a 3x. Now, think about your imaginaries. 5i and 5i. They need to be conjugates of each other. They have to be conjugates. That's the idea. Conjugates. One of them's positive, one of them's negative. Is a -25i squared, and I know that I squared is -1, so this is the 25 that I saw in the first place. One of them is +5i, the other one is -5i. Now again, you factored it, set equal to 0. You're going to use the ZPP, the zero product property. So 3x plus 5i is a 0, or 3x minus a 5i is a 0. We're going to subtract 5i. 3x is equal to -5i. We're going to add 5i. 3x is 5i. I need a little more room here. While I'm working on room, let's see what this look for relationships is. I bet it's talking about conjugates. No, it's actually talking about how you solved using square root methods. Should be mentioning the conjugate idea, but I didn't write this book. Maybe Pearson or somebody will pay me some good money and have me write a textbook. Next move is divide by 3. We'll have -5i over 3. Divide by 3, divide by 3. We'll have 5i over 3. And again, what's the relationship between these two numbers? What is the relationship between -5i over 3 and 5i over 3? They are conjugates. And you might be like, but I don't see a real number. Well, one of them is 0 minus 5i over 3, and the other is 0 plus 5i over 3. You can throw a 0 in anything, change it, so it's understood to be there. It's not one of those understood concepts. It's always understood you can add 0. Always understood you can add 0. Anyways, there is the Envision Algebra 2 version of complex numbers. It doesn't go into too much depth, which is good because it's not really a state standard in Tennessee anymore, but I'm still going to teach it. You'll appreciate that at some point in time in your life, probably college algebra. Anyways, I'm done. I'm out. Hope you enjoyed. Later.